So this is the notes for section 7.2, properties of powers. If you haven't done so already, please make sure that you stop the video at this time and read this section before continuing on with these notes. What I want to do first in this section is I just want to quickly run through the different postulates or assumptions that we make about powers, okay? And then at the end of the notes, I want to run through several examples that relate and put together kind of all of these properties and postulates. So the first one is the product of powers postulate, and that just says that if I have the same variable raised to different powers or the same power, it doesn't really matter. What I do is I take those powers and I add them together. So b to the m times b to the n is equal to b to the m plus n. Okay? So here's an example of that. X to the third times x to the fifth is equal to x to the eighth. Okay? Now for right now, it's really important that we also pay attention to kind of the stipulations on this. This is for any non-negative base b and non-zero real exponent m and n. So as we go through that, kind of pay attention to that piece as well. Okay? Next we have the power of product postulate, which just says that, hey, if I have the product of two numbers like a and b, and I raise it to some power m, that's the same as saying a to the m times b to the m. In other words, it's like we distribute the m to both of those, to both of the variables that are inside the parentheses. Okay. Now, once again, a and b have to be real exponents, or excuse me, have to be non-negative bases, and m has to be a real exponent. Okay. Next, we have the quotient of powers theorem, and that says for any positive base b and real exponents m and n. Okay. Notice how we've always been, these bases have always been for, positive values here. If I take the exponents and subtract them, that's how that works. So b to the m over b to the n is equal to b to the m minus n. In other words, I'm just going to subtract those exponents. So if we look at our example here, x to the 10th over x to the 3rd, I'm just going to take x to the 10 minus 3, or x to the 7th power. Okay? The power of quotient theorem. Okay, so if I have a quotient inside parentheses raised to some power, I can take, and once again, that idea of distributing that power to each of those values of the quotient, a to the n over b to the n. Okay, so an example here, if I have y over x raised to the 5th power, that's the same as y to the 5th over x to the 5th. Okay. The zero exponent theorem just says that if I take any number, it doesn't matter what it is, as long as it's non-zero. Okay, we can't take 0 to the 0, but any other real number and I raise it to the 0 power, that value will always be equal to 1. And we'll take a look at that in class in terms of why that is. But any number raised to the 0 power is always 1. Okay? And then the last one that we have there is the power of a power postulate. And that is, if I take a number, okay, once again, it's a non-zero real, a positive base and a non-zero real exponents m and n. b raised to the m, and then that quantity raised to the n is the same as taking those exponents m and n and multiplying them together. So x to the 3rd raised to the 5th is x to the 15th. Okay. Now you can think about that one. That's the one that people struggle with a little bit, and that's like saying, remember, if I say x to the 3rd raised to the 5th, that's like saying x to the 3rd times 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 x to the 3rd. And then if I were to add all of those together, that's the same as x to the 15th. So that's why that works. So I'd now like to be able to take a look at some of these example problems that we have on the second page of your notes. Number 1 just says solve for x. It says 18 to the 4th times 18 to the x is equal to 18 to the 12th. Well, I know that if I take 18 to the 4th times 18 to the x, I can add 4 plus x, and that's got to be equal to the power on 18 over here, which is 12. So when I do that, what I'm going to do is I'm going to just say 4 plus x is equal to 12. And if I do that, if 4 plus x is equal to 12, I can solve for x by subtracting 4 from both sides, and that's what I'm doing here. To go from 4 plus x equals 12 to x equals 8, I just subtracted 4 from both sides, and I have x equals 8. And it would make sense because 18 to the 4th plus 18 to the 8th is equal to 18 to the 12th. So in number 2, it says how many zeros are at the end of the number n equals 5 to the 5th times 2 to the 5th times 32 when n is written in base 10. Well, I want you to think about it from the standpoint of not just plugging that into your calculator and seeing how many zeros you get. I'd prefer to think about it from the standpoint of applying our properties. So let's look back at our properties first. I know that the power of a product postulate says that ab to the m is equal to a to the m b to the m. Well, I can go both ways with that. I can go from here to here, or I can go the other way. Okay? So what I'm going to do is I'm actually going to use the power of a product postulate, and I'm going to move backwards with it. So what I'm going to do then is I'm going to say, well, if I have 5 to the 5th times 2 to the 5th, I can write that as 5 times 2 to the 5th, or 10 to the 5th times 32. Now 10 to the 5th I know is going to give me 5 zeros. Therefore, the answer here is there will be 5 zeros at the end of that number. Okay? Now we can show that by looking at it from a calculation standpoint. If I look at that on my calculator, 10 to the 5th power times 32 gives me 5 zeros at the end of that number. So let's take a look at number 3 here. Okay, so if you think about that, we have 2 pages, 6 questions on each page, and each question has C possible choices. So if I think about it from the standpoint of each page has 6 questions, the different ways that I could answer questions on any given page would be C to the 6th power. And since there's 2 pages of questions with the same 6 questions, I can raise that to the 2nd power. So that would be a power of a power. Therefore, I can say C to the 6th times the 2nd, or C to the 12th power would be the number of different ways that I could answer that quiz. So in number 4, it says the mass of the Earth is 5.9 times 10 to the 24th kilograms, while the mass of Jupiter is 1.9 times 10 to the 27th kilograms. The mass of Jupiter is about how many times the mass of Earth? Well, to do that, really the question we're asking is, if I were to divide the mass of Jupiter by the mass of Earth, what is that number? Okay, that's really what I'm doing. And you can see, because this is 10 to the 24th for Earth and the 10 to the 27th for Jupiter, I know that the mass of Jupiter has to be bigger than the mass of Earth. Okay, so what I want to do is I want to do that division. So let's set it up that way, and then I'm going to put in each of those masses. So we have 1.9 times 10 to the 27th over 5.9 times 10 to the 24th. Okay. Well, what I can do then is I can take 1.9 divided by 5.9, and then I have 10 to the 27th over 10 to the 24th, in which I can use my properties of powers to help simplify that. So I have 1.9 over 5.9 times 10 raised to the 27th minus 24th. And then if I finish that off, 1.9 divided by 5.9 is about 0.3, not exactly, but approximately 0.3. And then that would be times 10 to the third power. So that's how much bigger that would be, roughly, the mass of Jupiter to the mass of Earth.